We are just constantly bombarded with claims. This is 99% effective, that's clinically proven, this reduces your risk by half. So how do you actually separate what's real from just, marketing fluff? Well, there's a really powerful statistical method for that. And today, we're going to break it all down.
Okay, let's take a classic example. You've seen this a million times on a bottle of something. A company makes this big, bold claim. Their new sanitizer kills 99% of germs. It sounds super specific, really scientific, right?
And that's the million-dollar question, isn't it? Do we just take their word for it? How can we, whether we're consumers or scientists or data analysts, actually check a claim like this? Is there a formal way to put it to the test?
And look, this is exactly why it matters. Because if we just go with our gut or make a wild guess, we're risking some really bad calls. In the business world, that could mean a terrible investment. In science, it could lead to completely false conclusions. We've got to have a better way.
And lucky for us, there is a better way, and it's called hypothesis testing. This is the solid, structured framework that lets us use data as our evidence to check out a claim in a really logical step-by-step way. So what is this thing really? Okay, at its heart, hypothesis testing is a formal procedure. We take a claim about a whole population, like say, every single bottle of that sanitizer out there, and we use a much smaller, manageable sample of data to help us decide if there's enough evidence to believe that claim or to reject it. Every great showdown needs two opponents, right? Well, in hypothesis testing, every test starts by setting up two competing statements. You've got the claim that represents the world as it is, the status quo, and then you have the claim that's challenging it. So this whole process boils down to two competing ideas. First, you have the null hypothesis. Think of this as the boring old status quo. It's the default position, what we assume is true until proven otherwise, kind of like innocent until proven guilty in a courtroom. Then you've got the alternate hypothesis. This is the exciting challenger. It's the new idea, the claim that we're actually trying to find evidence for. And here's the really important part. These two claims can't both be true. They are totally mutually exclusive. Either one is true or the other one is. Our job is to use data to figure out which one looks more likely.
Okay, so let's bring this back to our sanitizer. The null hypothesis, which we write as H0, is basically that the company is telling the truth. The sanitizer kills exactly 99% of germs. But the alternate hypothesis, or H1, is our suspicion. It's the challenge. What if it actually kills less than 99%? Our whole goal here is to see if our data gives us enough reason to reject that original claim.
All right, so we've got our two competing claims set up. Now, how do we actually decide which one wins? Well, we need some clear rules for making that decision. And this is where two really important ideas come into play: alpha and the p-value.
First step is alpha, also called the level of significance. The easiest way to think about this is it's your line in the sand. It's the standard of proof you decide on before you even peek at the data. You're setting the bar for how strong the evidence needs to be to convince you.
And then there's the p-value. This is a number you calculate from your data, and it's basically the surprise factor. It tells you how weird or surprising your results are, assuming that the original claim, the null hypothesis, was actually true. And this is the golden rule right here. The lower that p-value, the more surprising your data is, and the stronger your evidence is against the status quo. A really, really small p-value, that's like a giant flashing neon sign telling you that something's up with that original claim. All right, we're almost there. We've set our line in the sand with alpha, and our data has given us our evidence, the p-value. Now it's time for the final verdict. And you know what? The rule for deciding is incredibly simple. It all comes down to one little comparison. You take your p-value, you look at that alpha you decided on earlier, and you just ask one question. Is my p-value smaller than my alpha? If the answer is yes, you reject the null hypothesis. That's it. So what does that actually mean when we reject the null hypothesis? It means we're saying that based on the evidence from our data, we have enough statistical muscle to support the challenger, the alternate hypothesis. For our sanitizer, it would mean we've got some pretty solid evidence to back up our suspicion that, hey, maybe it kills less than 99% of germs after all. So big picture, why go through all of this trouble? Because this whole framework gives us a structured, repeatable way to make decisions based on cold, hard evidence,
not just a gut feeling. It's how we navigate that huge ocean of data and arrive at a decision we can actually stand behind.
When you boil it all down, hypothesis testing is just this incredibly powerful framework. It gives us a formal way to challenge assumptions, it keeps us from making bad calls based on feelings, and it lets us turn a vague claim into something we can actually test. It's a critical skill for anyone trying to think clearly in a world just drowning in data. But let's be real, no method is foolproof, right? The evidence we get from a small sample can sometimes point us in the wrong direction. And that leaves us with a really interesting question to chew on. What happens when the data leads you down the wrong path, when your test makes the wrong call? And how would you even measure that risk? Something to think about. Thanks for joining me.